Looks like the gang's all here. So just as a matter of review, and these are pretty much every physics textbook has a table like this somewhere in it. So obviously it's to your benefit to write, since the human brain is wired to learn this way. But just to kind of recap the collection, Gauss's law for electric fields is where we first started talking about flux. If you have a Gaussian surface, and if there's flux going into it or going out of it, just a number of things are true. Either it encloses a charge or it doesn't. If it's going into it without exiting it, or only coming out of it, then there's a charge enclosed. Otherwise, there's not charge enclosed. The magnetic field, same sort of thing. There's also no magnetic monopoles, and that's because of the structure of magnetic fields, but we'll move on. Faraday's induction law, we've been covering that. But these English statements, Faraday's induction law says an electric field is induced by changing magnetic flux. The Maxwell-Ampere law is the reverse of that. A magnetic field is induced by changing electric flux or a current. So the main events are about how flux changes induce other flux changes. All right? But obviously conduction current will do that as well. So Maxwell's equations cover a lot of ground in electrodynamics. So if you were going to be a physics major, then you'll take 4 semesters of physics again, and you'll take a whole course on electrodynamics, and you'll take this to the next level, mathematically and theoretically. And then you'll do it again in grad school. So not many people become physicists. I've only had 1 or 2 people in the 10 years that I've been here even declare that. So I think 2 people now. All right, so those are Maxwell's equations. They're in your book. Google them, buy a t-shirt, get a coffee mug. They all say the same thing, all right? There is a slightly different form when they're in differential form, like with divergence and curl and whatnot. So you might see a slightly different vector calculus version of them, but it's the same business. So a question to ask is, does an EM wave satisfy Maxwell's equations? And I think, hopefully the obvious answer is yes, otherwise why would we have a lecture on it? Okay, but let's prove that that's the case. And so what I'm going to do here is attempt to draw. I'm going to draw a Gaussian surface. And in this Gaussian surface, we're going to place an electromagnetic wave. And so I'm going to put an axis system. So it'll be my z-axis, that'll be my y-axis, and we'll have an x-axis coming out of here. So this Gaussian box, and what we can do is we will put some electric field and some magnetic field waves that are traveling along this x-axis. So as a matter of fact, all electromagnetic waves are what we call transverse waves, meaning 2 planar waves that are at right angles to one another and propagating in at a direction at a right angle to that. What do I mean by a planar wave? A planar wave is a wave that's in a plane. So like, for instance, the electric field wave, so we're having this is going to be a waveforms traveling in those planes. So in the XY plane is the electric field vertically. In the XZ plane horizontally would be the oscillating magnetic field. And they're in sync with one another, they're in phase. And meaning their peaks are at the same time and their valleys are at the same time. All right? And they propagate through space along a direction perpendicular, so it's a cross product kind of thing. All right, right hand rule sort of business. And so what we have here, so E ends up being the same on top and bottom of the box. So that implies that the electric flux is 0. Okay. B, same top and bottom of the Gaussian surface. So the magnetic flux is 0. So Gauss's laws check out. Okay? And everything that goes into the box comes out of the box. Net flux is 0 for the box. Yay. Now a little bit harder wave to draw. And this is where things begin to get thick. So here's a three-dimensional plane, or system rather. And I could define a first point X that I want to deal with, and I can put an electric field vector in the XY plane going vertically. I can then have a second, and oh, by the way, that means that there's a corresponding magnetic field vector in the XZ plane. Now, if I pick another point down the road here that's basically X plus delta X away, and let's say that at this point the electric field has increased, so I have E plus delta E. Well, then I'm going to have a corresponding B plus delta B. And so what's happening is there's a sinusoidal function that's associated with each one of these waves, and this will keep going back and forth and back and forth. In fact, all right, so these waves will go through space changing, and so what we need to do, we're going to need to pick a path in the XY plane and apply Faraday's law to that, then pick a path in the XZ plane and go through the same motions, and what we're going to find, we're going to retrace the steps that Maxwell did to determine that the speed of an electromagnetic wave is one and only one speed, the speed of light. Necessarily so, all right? So, so these fields they're propagating sinusoidally in the XY plane along the x-axis, the electric field sinusoidally in the XZ plane along the x-axis, and it always takes time to change position, all right? And so this is the kind of the nature of the way these waves propagate. So you have this picture hopefully in your mind or on your paper, and so I need to be, I wonder if I can scrunch this. I haven't tried this before. No, that's not what I want. Oh well. Do anything and make my path. So I'm going to create a rectangular loop Okay? So this is going to be my surface, the path. I'm going to go A, B, C, D. All right, and the reason I'm going to go A, B, C, D is there's magnetic flux going through that space. And the right-hand rule, like the current flow one, tells me I should curl counterclockwise. Tells me that should be, so how do you pick a right integral path? You use the rules that apply to these sorts of things. And so the right-hand rule would tell me to go counterclockwise. So I'm going to do A, B, C, D. And D to A is because you get zero contribution along those paths. All right? The dot product is zero there. We're dealing with the height, we'll just call the height H. Okay? Again, this is a standard treatment. I have half a dozen books, and there's probably 3.5 versions of this that are all fundamentally the same. You won't find a really fundamentally different treatment in any textbook. So all I'm really doing here is trying to expand on those explanations a little bit. So Faraday. So if I apply his rule, what do I have here? This is just an integral along a closed path. So what I want to do here is take advantage of the opportunity to have an English statement for every mathematical one. All right, the math will be relatively simple, but let's try to obtain a better feeling. This part right here, this is going to be the electric field changing in space. Some space somewhere. And time rate of change of flux of magnetic. Just mathematizing, I'm just translating the math into English. You're stating the law, maybe more crudely than the wordsmith versions. But to kind of pull all of that together, adding up all of the changes in the electric field along a closed path is equivalent to the time rate change of magnetic flux. Now, part A, I'm going to just do the EDS part. Okay? There are vectors. Be careful. What would the EDS part? Now, what I have to do is go back to the picture here before we have the advantage of having one piece of paper. I got to switch screens. So this means that I'm going to have, now the electric field is going to be essentially constant along every little ds because these differentials are insanely small little chunks. So I can pull E out in front of my path integral, and I'm going to have an A to B ds, and I'm going to have a C to D ds. The reason why I don't have B to C, So this will result, well, I'm going to do it underneath since I'm running out of space. So I'm going to get a summing up. So I'm going from that A to B. And that's the electric field there is actually E plus delta E. Oh, and I forgot to, so times the height, all right? And then coming down the other way, it's just E, because that's the first one at position X, times the height as you're summing down. So since I'm summing down, it's minus. So here's my summing up, summing down, all right? And so in the end, this just works out to be H delta E, or if in calculus terms, it would be an H dE, the differential. So I'm sort of blending the algebraic viewpoint with the differential to get us to a calculus version, okay? So that just tells me what the left-hand side of the equation is. The right-hand side of the equation, the minus change in flux per unit time. Remember, flux is always an area times a field sort of thing, so I'm going to have that area, and I'll just use deltas here, delta B per delta T, just to kind of keep it consistent with the picture that we're referring to. Well, what's the area? Well, the area is going to be the length times the width. And one of the length dimensions of our box was h, and the other dimension of the box was delta x. And we had our delta b, delta t. And so in calculus terms, that means we have an h dx, db dt. So our end result, EDS gives us an HDE, and dBdt gives us this HDX, or phi dt gives us this other one. So Faraday's law applied to a path slash surface, if you will, for the electric wave propagating sinusoidally in the xy plane along the y-axis, we have this result. Now, the thing is that these two things are equal, okay? So, since I'm out of space, I'll continue on to the next page here. So, we know that A equals B from our equations, and so that means HDE will equal minus H dx dB dt. So the h's drop out, and you get a nice, pretty differential equation. dE dx equals minus dB dt. So I think it's important that you have a decent interpretation of what that means. Left-hand side, the position rate of change of the electric field is equal to the opposite of the time rate of change of the magnetic field. So a changing electric field in space is in some way equivalent to a changing magnetic field in time. It's an interesting equation. The way one thing changes in space results in the way another thing changes in time. All right? Now, one thing that we have to be careful of, though, is both EY and B sub z, so E is in the y direction, its amplitude. The amplitude of the magnetic field is in the z direction. Both of them are functions of x and t, which means we need to talk about partial derivatives. So technically, we should be writing it that way. Now this is where eventually vector calculus, you get into your div, grad, curl, and all that. We'll dance along that line slowly. It's easier to build up from the algebra and make sense of the calculus. And not everybody's had the full-on vector calculus game going for them. But wait, there's more. What in the world would the partial of the electric field with respect to x mean? Good question. I'm glad you asked. So, let's see. I'll call this C. What is dE dx? Well, it would be the partial with respect to x of whatever E is. Well, you did see that it was a sinusoidal function, correct? Correct. Well, the amplitude of that function is the maximum voltage, our electric field strength, okay? And then this characteristic function for sinusoidal function, it's always the sine of the phase angle, which the phase angle is the wave number times x minus the speed times time. And I guess the thing to remember, recall that yx of t is amplitude sine kx minus omega t. So that's just, you're supposed to remember all that from your pre-calc days, right? But we know how that goes. Well, this is a relatively easy derivative because the rules for differentiation don't change much with partials. It's just that now you're only differentiating with respect to that one variable. You ignore the other variables, you treat them like constants. So that means my dE dx partial wise, the constant on x inside of the phase angle, that will come out, the wave number. That's what, it's really a kappa. It's a kind of a short capital K. E comes out as a constant, and the derivative of sine is cosine, and the phase angle doesn't change. So that's what the partial of E with respect to x is, calculus-wise. Get my thing back on there. So there's that. Then we need to do the dB dt. So I'll call that part D. The minus dB dt will be minus ddt of the magnetic field. And again, it's going to have the same characteristic functional form. You'll have B max, maximum amplitude of the magnetic field, then the sine, same phase angle business, generally applicable. And again, we're going to get, so out of this, we'll get a negative of, because that minus omega comes out from the part of the phase angle that we're differentiating with respect to. And we're going to get our B max sticks around as a constant. Derivative of sine is cosine, kx minus omega t. Well, C equals D, okay, because these were two parts of an equivalence. So what am I going to get? I'm going to get that wave number with the electric field cosine of kx minus omega t is going to equal omega B max and the same business. Well, The sinusoidal part of the functions are identical, so they drop out. And you get these wave properties. If I put the wave properties together and I put the field effects together in relationships, I get this. You probably have forgotten, but omega is equal to 2 pi times frequency. The wave number, even more people have forgotten, is 2 pi per lambda. And that means you get frequency times lambda. Well, guess what that is? Lambda is a wavelength, a distance. Frequency is inverse seconds per unit time. That's speed. That's linear speed, in fact. So let's pause for a second here and consider the fact that we have now found the speed of this wave is simply the ratio of the field strengths of the two planar waves comprising the transverse wave. This doesn't alone, this does not prove that the wave is moving at a constant speed. However, you should suspect that it's moving at a constant speed given that these fields are in phase with one another. Okay? So we'll see how that works out, but this is just part one of how we get to the fact that this wave speed is the speed of light. So we have good reason to suspect that it's constant. So one more time, drawing the wave, because now I have to flip it down into the other plane to do my math. So I have E, I'm going to have E plus delta E, I'm going to have B plus delta B. This is my X spot, this is my X plus delta X spot there. And so now, if I flip the rectangle down to be here, and so I'll do the same A, B, C, D business as before. Now I'm going to do my loop around there, but I'm going to use the Maxwell-Ampere law because now I'm talking about electric flux going through my surface. So think about it. This is laying in the plane of the magnetic field oscillation, and supposedly electric flux is going through it. So that means switch gears from Ampere's law, which applied to the last one, to our Faraday's law, to the Maxwell-Ampere law in this one. All right? And again, that law says that the dot product of BDS will be, and in this case, well, I'll go ahead and write it. We know that we have a changing flux. I should write the current part, the conduction current, but it's 0 because there's no conductor here. All right? So Maxwell-Ampere this is what we're gonna do the same business. It'll go the same way as the other one, just with some slightly different pieces in the puzzle. So let's say so part A, the BDS business. So same deal. I'm going to have BH minus the B plus delta B H, and that's going to equal a minus delta B times H, which means in calculus terms a differential on B times H. Got the same structure before from the electric field one, so these are really not going to be different, fundamentally speaking. Part B, the mu naught, epsilon naught, electric flux in time. Again, remember that flux is an area computation and then the change in the field associated with that area. And here we're going to get, well, our constants stick around, but the area, just like before, it's going to be the height of the box, and it's still changing along the x-axis. So it has that in common with what we did with Faraday. And we're going to have a dE dt, and of course this, in calculus terms, would be an h dx dE dt. So the BDS part is a minus dBH. The displacement current part is all of that. Looks very much the same as what we did before. And I'm going to scooch to a new screen since I'm kind of a base. So basically, once again, the A equation equals the B equation. So minus the differential on the magnetic field times its height will equal all these constants jammed together, h dx, and that differential on the field. Once again, h drops out, and you get a minus dB dx equals mu naught epsilon naught dE dt. So this is different. Last time it was the electric field changing in space on the left-hand side and the magnetic field changing in time on the right-hand side. So we literally come full circle using a rectangle. All right? Changing magnetic fields in space produce changing electric fields in time, and changing electric fields in space produce changing magnetic fields in time. So these two laws are the kind of the inverse of one another, and they tell us an interesting fact. So Maxwell would have gone, aha, one field change causes the other field change, which in turn causes the other field to change again, which it causes the other one to change again, and it keeps going back and forth and back and forth. And the only way it would stop is if there are so many interactions that all of that energy gets transferred to other things. So if there's no interactions, it keeps going on forever. But if it interacts with matter, which it inevitably will do, then it's going to run out of steam eventually. All right, so we have this. And guess what we got to do? Because these are, since, EY is a function of x and t, and BZ is also a function of x and t, that means we need partials instead of regular derivatives, which means we go through the same motions that we did before. Now, instead of bothering writing all of that out, you can go look this up in a book if you want to, but I'm just going to cut to the chase. We're going to get E over B equals 1 over mu naught epsilon naught V. So the same rigmarole of putting in sinusoidal functions and differentiating them partially with respect to x and t will lead to the fact that the ratio of E to B is another thing that involves V, but not directly. Okay? So this is the Maxwell Ampere speed relation. E over B equals B, or V, that's the Faraday speed relation, which means V equals 1 over mu naught epsilon naught V, which means we're about to find out that the speed of this wave is constant because it's built out of only constants, fundamental constants of the universe, 2 of 6. All right? So another clean screen here. So Faraday's E over B has to equal Maxwell Ampere's E over B, which means V has to equal 1 over mu naught epsilon naught V, and that means V squared is 1 over mu naught epsilon naught, which means V is 1 over the square root of the product of those two fundamental constants. So plugging and chugging that, mu naught is 4 pi times 10 to the minus 7 Henry, well, I think it's Henrys per meter in one viewpoint, but it's newtons per amp squared in this one. And epsilon naught is 8.85 times 10 to the minus 12 newtons per amp squared. You do all of this stuff and you basically get 3 times 10 to the 8 meters per second. It's actually 2.9968 something or other, blah, blah, blah. So an interesting result, these laws that were created empirically by the observations, led to hypotheses, led to equation building, testing, etc., etc. The mathematics, bringing them all together, if Maxwell hadn't come up with displacement current, we wouldn't be, somebody else would have had to do that. But Maxwell said, wait a minute, there's something missing in Ampere's law, figured out what it was, stuck it in there. It ended up making the law more widespread, covers all situations instead of just one. And then the rest is math. We haven't done much physics today. We did the math associated with that physics. And so to come up with a result that the ratio of these two fields is always the same ratio no matter what your perspective is, and that it boils down to the product of two universal constants. And they're the two universal constants that make sense, because the magnetic one deals with how does the universe tolerate magnetic field, magnetic flux, and the other one is how does the universe tolerate electric flux. So the two constants that are all about what we're paying attention to absolutely define the speed of this radiation, this electromagnetic wave, light. Light is, the electromagnetic spectrum could be called light, all of it light. Very little of it's visible to us. One little sliver, okay? We see like from just under 400 nanometers to, I think, just under 800 nanometers wavelength. And there's a lot of space on the spectrum, all right? From microwaves and radio waves and X-rays and gamma rays, et cetera, et cetera. More or less energetic, more or less frequency, et cetera, et cetera. So